in the hopes of promoting the awareness of the unlimited energy that electrical engineering can provide us. I hope this video is at least entertaining or amusing, if not also educational and edifying. But certainly I do not hope that this video is harassing in any way, shape, or form, because I know a lot of people would like to hold their ears whenever they hear the word over unity or free energy, because it hurts their ears, literally. So here we go. We'll plunge right into it. This is a theoretical explanation as to why it can be possible to make a solid-state electrical device with no moving parts create seemingly more output than input. Here we go. It all hinges on what we can do with current, not voltage. So we're not making more wattage necessarily, although that it'll look like that, the end result. But we make more current, or we don't make, let's let me back up a bit. More current appears in the circuit than was there to begin with. Where it comes from, that's a whole nother topic about duplicating a wave, but we won't go there. Now, electricity is like a football team in which you have a lot of players, and a number of players, or any kind of team sport, a number of players just sit out on the bench the whole season and they don't play unless called upon to do so to fill in for somebody else. So it doesn't matter then whether we say energy out has to equal energy in, because we're not making use of all of it anyway. But also it's a team effort in which all the team members participate and contribute, and they're all important, the ones that participate, and they're all important, the ones that don't, but stand on the side and wait. And that's the way it is with electricity. It's not a singularity when we talk about it. So when we say energy in has to equal energy out, that's so bogus, because it oversimplifies the situation to the point of suppression. Literally. It's to suppress talking about it or thinking about it, which is what I've done, only to discover that I probably already know this stuff deep somewhere in my soul, and it's just a question of having been devoted enough to apply myself that I'm able to figure out the details with the help of the simulator and information online and interacting with a few people. So, what will I have done in this latest circuit at is.gd/Syncur, SYNCUR, Samuel, yesterday, Nancy, chastity, understanding, relationship. Those 6 letters after the is.gd. is.gd as in is good. It's a good link. That circuit has a battery sandwich, a vertical stacked, in terms of the diagram, it's a vertically stacked sandwich of 2 batteries surrounding a capacitor. And that is my make-do workaround solution to simulate what I talk about in another video that I put on YouTube. I won't tell you the link to the video because some of you don't like the idea of watching me videotape shirtless. Oh my God, he's got bare shoulders! So I'll spare you. But I'll just, summarize, so you won't have to go there. I suggest a new type of capacitor battery blend, and it turns out people are already selling capacitor batteries. I don't know if they're structurally the same as what I'm suggesting, though, and that is to take a capacitor design and modify it such that the 2 plates on either side of the dielectric are not of the same material, but are of different material. And actually, now that I think of it, there is one that already exists. I just remembered now. A guy in England suggested its use, I believe. It's iron on one side and aluminum on the other. There you go. So already we have a galvanic response creating a battery type difference between the two terminals, a voltage difference between the two terminals, but instead of electron migration taking place internally to be able to complete that internal circuit so as to allow current to flow from the battery outside the circuit, we block it with a dielectric so that it's a capacitance situation, and now we have a voltage reference that cannot drain its voltage to turn it into current because it's prevented from doing so, but it still provides the presence of voltage, and that's what I want to do. But so in the simulator I can't do that, so I have to do a workaround solution of creating a battery capacitor battery sandwich, and it works pretty good, provided I take into consideration and apply the principle of one of Tesla's patents, and that circuit, the shortcut is is.gd/AC plus DC. And what Tesla did was he fed AC into a subcircuit that had two batteries and two lamps, and it adds the energy of the AC input to the DC portion so that the lamps can light. So in that demonstration, the lamps require 120 volts, or what is it? 120 volts in order to light. But each of the two batteries is only 70, and there are two lamps. One, well, how does that work? Oh, I'll try not to understand it. I can't do the math at the moment. I don't know why that doesn't make sense. Anyway, it's got two lamps that require 120 volts nominal voltage to light up, and two DC batteries, which are in series when you think about it, because it goes around in a circle. So I don't understand that. Well, anyway, you go there and you see, and then there's the AC input on the outside, and it's pretty clever. So I thought I would use it, but I couldn't. But it inspired me, because what happens is, in the Synthesize circuit, the AC from the two aerials comes in, and it shimmies back and forth through that battery capacitor battery sandwich at a low level of amperage, no higher than 4 amps or less. It could be half a micro or 200 nano amps or whatever. It's very low, considering the fact that each of the two batteries on either side of that capacitor are 108 volt unit or pack of multiple units to make 108 total on either side, so that there's 216 lined up in series with that capacitor. And the capacitor in the middle is 10 millifarad I chose to use because it seemed to be best. Now that's to the left of a transformer, just a standard transformer, 1-to-1 ratio, but, well, not standard actually. It's a 1-to-1 ratio, and the inductance on obviously on either of the primary or secondary wire coils is 2 henries, because I needed to make it, each of those two coils, the same inductive value as the load, which I'm going to get to shortly where that is, and the load is also 2 henries. And I'm just guessing maybe the motor in my electric car, my RAV4 EV from 2002, is overall a total of 2 henries of all the coils added up together, if they were, like, combined somehow. The total production of inductance is 2 henries. I'm just guessing. I don't know what it is, because it's not on the spec sheet. Usually you don't find something like that on the spec sheet for a motor. I don't know why not. I don't know why it's not there. Anyway, so I'm massaging this battery capacitor battery sandwich with 4 amps or less, and with an AC sine wave coming in from the two aerials that I have to the left, so of that sandwich. So you've got the transformer, that's the divider, of the two halves of the circuit. The power side, collection side, or whatever you want to call it, is on the left, and the load is on the right, and the controller is also on the right. Anyway, I'm describing the left-hand side, but first of all, the transformer is a weak coupling, and this is crucial and vital for the operation of this device to operate at all efficiently, is that it have a weak coupling. And at first I chose 0.5. You know, a simulator, normally the standard default is 0.999, but I made it 0.5, and then I found that it even gets better if I make it 0.1. So there's probably no limit to how efficient this circuit can be made simply by reducing the coupling coefficient on the transformer. The efficiency can be improved. And it's reverse logic to what we would think, you know. But, you know, there's nothing about free energy that's normal. If you have to accept it into your life, the only way to do so is Alice in Wonderland through the looking glass. Nothing is as it seems. Alright? So, we've got the transformer in the middle, and then we have the battery sandwich across the left-hand coil. Across meaning it's connected to both terminals of the left-hand coil. And then coming out, we've got two leads from each of those two junctions, and those two leads might have a little tiny resistor of 1 micro ohm each, but then they terminate in two aerials, and the size of the aerial matters because, or not the size so much as the surface area, because we want to maximize surface area. We also want to, it would be nice to elevate it, you know, but then if you elevate it, you got, you know, problems attracting lightning and whatnot. I don't know why people are so I guess you've got to have a grounding protection in case there's a surge. It should go to ground, but we don't want them to be grounded. These are not grounded aerials. They're floating above ground. They have to be isolated from ground unless struck by lightning, okay? And the more surface area, the better. And so the example I take, design parameter, is an example from C. Earl Aman. That's spelled A-M-M-A-N. So Apple, Mary, Mary, Apple, Nancy. C. Earl. C is the letter C as in Charlie. I don't know what his first name is. And his middle name is Earl, E-A-R-L. And there's not a whole lot of information on the guy and what he invented, but there's enough to inspire me. So, he used bronze hollow spheres on either side of the front end of his car, positioning each attached over the headlight of his car, and he managed to drive his car around, his EV, without the need for a rechargeable battery pack. How he did it, I have no idea, but that's part of the clue of how he did it, because that's part of the circuit. So I took that into consideration, and I realized I needed to make a circuit of two aerials, not one. You know, this idea, oh, you use an aerial to pull in energy from your environment. Yo, okay, but how come you're using only one? It's okay, it's not grounded, fine, but why one? Two is better. And you position them in such a way that the air flows between them to increase capacitance, to increase insulation between them, or increase resistance to the point of as close to infinite resistance as you can get, so that it becomes a capacitance relationship between them in space rather than merely a resistive one. Because if you've got an ionic channel, then you've got conductivity to some degree along with resistance to some degree, and we don't want that. If you can't avoid it, then whatever. But you try to raise resistance between them in space as much as you can to infinite resistance, so that you have capacitance alone left remaining, and no and no conductivity whatsoever. And the best way to do that is to position your two aerials on a car, let's say, perpendicular to the line of airflow when you're driving. And the faster you drive, the more power you need, right? But the more capacitance, the more resistance you're going to get between those two aerials. And they're not elevated much from ground, a couple feet at best. But they're hollow bronze spheres. And the bigger they are, the better. But, of course, they're going to have wind drag. So maybe they shouldn't be solid spheres. Maybe they should have a wire mesh. But even that will offer resistance, depending on the size of the mesh. So you might have to open it up a little to let the air go through. But maybe that's no good to let the air go through, because maybe you have to encapsulate the air on the inside to create a charge on the inner surface of that sphere, of sufficient inner surface area for that to really work. And because we're using these as voltage references for the circuit, and you have to be able to change over time, because they're going to alternate. When one is positive, the other is negative, and then it flips. Because this is an AC circuit to run an AC motor. I don't know if the alternation, the cycling, is regular rather than slightly irregular. I can't vouch for that. It will change over time depending on the controlling capacitor on the right-hand side of the transformer, which I haven't gotten to yet. But this is, so far I've described everything on the left hand of the circuit, or left-hand side of the transformer, and the transformer itself. Now, the right side of the transformer, the two leads of that coil, the right-hand coil, is connected to another, it's connected to a capacitor, another capacitor type situation, but just one capacitor. And that capacitor is 10 farads. But it's a very special capacitor, and you have to go and buy it and spend money. It's a vacuum tube variable capacitor invented by Nikola Tesla, in which he filed for a patent in 1896, but on Wikipedia the article doesn't say he received the patent. So I don't know. But it did become commercially available a year before his death. He died in 1943 and became commercially available in 1942. Now, that capacitor, the shortcut to the Wikipedia article is is.gd/Tesla cap. So Thomas, Edward, Samantha, Larry, Apple, Charlie, Apple, Peach, Tesla cap. So now that cap is variable, and you're going to be varying it to a high maximum, probably no more than 10 farads, and a low, you want to be able to go down to a low of 10 millifarads, and anywhere in between, because you're going to be varying it, jimmying it up and down, up and down, up and down. And it has a very interesting property when you do this in the context of this circuit. Gradually at first, without perceptibility at first, you are actually increasing the level of amperage in this circuit far beyond the voltage level of this circuit. And if not for the battery capacitor battery sandwich on the left hand side, which will actually add voltage to the circuit, because it's lending its voltage without spending it, because it doesn't. When I scope that sandwich, or actually when I scope the topmost battery, so one battery on that battery capacitor battery sandwich, it merely gets massaged by a sine wave of amperage, 4 amps or less, and it never is exclusively either positive or negative to indicate whether or not it's exclusively charging or discharging. It's always doing both alternately in equal amounts, and so it never changes its state of charge overall over time. It simply gets a nice little tickle to keep it conditioned, to keep it convince it that it's being used, because batteries like to be used, and they age more quickly if they just sit there on the shelf and don't get used, or worse, sit in an electric car or in a circuit connected but don't get used. So it maintains the state of charge, the health of the battery, its state of charge as well, and without using it. So I'm literally in that mock-up, in that workaround solution, I am using the voltage of that those 216 volts but borrowing them, but I don't use them. I don't drain them to create current, because the current is done by the rest of the circuit. I merely get voltage from that sandwich, which is what I want, because I have to raise the voltage because the impedance is so low on this circuit. Otherwise, it's ridiculous, and most standard motors require at least, a reasonable amount of voltage. Unfortunately, in this simulation, it still lags. The voltage level lags the current by a factor of about 2/3. So whatever current you have, measured in amps, the voltage measured in volts will be about 2/3 of the amps, which is, better than far less, which is what I was getting. Actually, without that sandwich, I wasn't getting any AC voltage at all. It was I was, but the AC waveform was totally different than the current waveform. It was so slow, such a long wavelength, and it had absolutely no relation whatsoever to the change in state of the current, up or down. It just continued to do its thing and slide slowly downwards in the negative. In other words, it's upwards in terms of absolute value, absolute magnitude, but in the negative direction, the negative polarity. But without that sandwich. But with the sandwich, I get the voltage more in sync with the current, and I get to raise it to be a little bit more closer, a one-to-one relationship between amps and volts. And that's pretty good. So I consider that sandwich to be a good workaround solution, because it pretty much does the job. But it helps to use, if you're having trouble, let's say in a real-life build that you're testing, then it helps to increase the amount of volts there. So I chose to raise, I started out at 72 volt for each half, sandwiching the capacitor in between, and it wasn't enough, so I raised it to 108, and it pretty much did a pretty good job. So, but if it's not good enough, then just raise it some more. So you need to have a battery pack. You can't throw it away. You got to have that heavy paperweight, because in my car it's 1,100 pound paperweight, 24 12-volt modules of 95 amp hours each, nickel metal hydride, centered underneath the belly of the car. But you got to have it, but you don't have to use it. You just maintain it, condition it, and borrow and reuse that voltage. Okay, so this controlling capacitor, you jiggle it, you what's the word I'm trying to think of? Jimmy. You try to jimmy it. Sorry, James. You try to jimmy it up and down, and that actually raises the amperage of the circuit, and it's amazing. But it satisfies the criteria that Eric Dollard has stated in the synthesis of current. In the synthesis of electricity, he calls it, but I say synthesis of current because I'm reusing the voltage. I'm not synthesizing that. I'm borrowing or reusing the voltage, but I'm synthesizing current from its constituent parts of magnetism and voltage. But I'm using mostly, I better not get into that, because I don't know the physics too well. That's as much as I know. So somehow or another, because he says you synthesize electricity from its constituent parts of time, electrostatics, and magnetism. And more specifically, if you vary the electrostatic field in which is immersed a magnetic field, then you synthesize electricity. And I suspect that's what's happening. By jimmying the capacitor up and down, you change the capacitance of the circuit, which in turn changes its electrostatic behavioral characteristic. And you've got it connected directly to the transformer coil, the right-hand coil, and therein it's having an impact somehow on the magnetism of that transformer to somehow synthesize more current. Okay, so now connected also to those two junctions of the controlling capacitor on the right-hand side, we have two leads that go, actually 4 leads, 2 each. One goes to a starting battery with a switch, and the starting battery I made at 6 volts because that's what the kind of battery that was under the hood of a standard internal combustion engine in the 1930s, namely the Pierce Arrow that supposedly Tesla demonstrated an EV conversion of. And by the way, a Pierce Arrow is over 4,000 pounds in weight, in curb weight. So he had to have a powerful AC motor installed, according to that story, to be able to push it around on the city streets at 90 miles an hour out on the country road. So you had to have a pretty good power system to power this thing, if indeed the story is true. And I take it to be true, and I ran with it. So we have two sets of junctions on that. So we have really three subcircuits, or three subcircuits on the right-hand side of the transformer. And we only have two on the left-hand side, but we have three on the right-hand side. But one of those three we don't use except once in the very beginning from a cold start. And that's the 6-volt battery with a switch. And it's a snap switch because we only want to we only want to drain that 6-volt battery for an instant. So, and on that, besides a switch, on-off a snap switch and the 6-volt battery, also in series is I use a 100 mega ohm resistor to bring the amperage down, the contribution of that battery down to 60 nanoamps. That's what I see on my scope. So I'm draining that battery only when I need to from a cold start, and only 60 nanoamps at that, a spike of 60 nanoamps. And that's pretty good in terms of actually, see, this is how I think. Never, like wealthy people, don't spend your own money when you want to invest in wealth, spend somebody else's. Well, when it comes to spending energy from a source outside the circuit, namely a voltage source, that it's going to cost us, such as a battery, I try to spend as little as possible and only when necessary. And when the circuit is live, if it never goes dead, or until it goes dead, let's put it that way, until it goes dead, I have every opportunity to keep it alive forever, no matter what the load up to a reasonable limit. There's always reasonable limits in all these things, because if you go beyond the limit, the circuit will die. Duh, because you got to take the trouble. And when we get to the second subcircuit, the load circuit, we also have to have an on-off switch, but not a snap switch. This is a switch that engages on or engages off the load coil, which in this case represents the motor coil, because we can't do two things at once in the circuit. We either drive the load with the energy from the circuit, or we disconnect the load from the circuit and raise its power level. And then when we get it raised to where we want it, then we engage the load subcircuit to provide power to the motor coil. But now we're not jimmying the controlling capacitor, its capacitance value up and down. The variable vacuum tube capacitor. We don't jimmy it up and we don't wiggle it up and down. Because you won't, not because it'll harm anything, but because, well, I don't think it will, I don't know, but but because it won't do anything. You have to disengage the load to be able to do anything. And the starting battery on the other of the three subcircuits on the right-hand side of the transformer is only engaged once, and then only for an instant. So the only subcircuit on the right-hand side that is engaged all the time is the controlling capacitor. But we leave it alone when we're driving. But when we want to raise the power that we're delivering to the motor, we have to disconnect the motor momentarily as we jimmy the controlling capacitor up and down. Now, it turns out that there are different factors that we can help to make the motor coil sustain its level of amperage and voltage for an extended period of time. And by the way, the voltage drops more quickly than does the amperage. So I ran my simulator at a 1 second time frame, and that's the other thing. This circuit is so good that you don't have to run it at any particular time frame in order to get the free energy result. Normally when I do circuits simulations, I have to run the simulator at a very small time frame in order to get free energy to occur, because if I change, and then I'll get a narrow window, because if I change the window, it's almost as if I'm looking for a sweet spot, that somehow the circuit has a resonant sweet spot that the simulator has to be in touch with, in sync with, in order to get the free energy anomaly to occur. But in this circuit, it's not there. It doesn't happen. There is no sweet spot. You don't have to look for one, because there isn't any to look for. So you can run it at any time frame you want to, because there is no resonant point to increase efficiency. There are other factors to increase efficiency, namely the, well, I'll let you, I won't get into that. But I ran it for something like, oh, what was it, 16 days or 6 days, something with a 6 in it. I think it was either 6 days or 16 days. And it still had, you know, it started out at 230 or 240. I want to say 240 amps and 150 volts, or somewhere around there, 150 or 160. 240 amps and 260 volts. And the volts dropped after the end of those multiple day periods. It dropped to around 30 volts, which is pretty much a big a drop. But the amps only went down to about 208, I want to say, somewhere around in there. So it really sustained its amperage very well. It's the voltage, unfortunately, which drops so precipitously. So that's that can probably be fixed somehow. I don't know how, but you know, I've only spent 2 days on this circuit, you know, so I'm pretty good, aren't I? I can whip these things out. You know, I spend a lot of hours, and I push myself. I got swollen feet yesterday, anyway. So that pretty much completes the description of the circuit, and I hope that you try it out and see if you can get it to work as well as it did in the simulator. I don't see why not, because I tested it under 2 different simulators. The plain simulator of Paul Falstad, but then the one that I altered it, in which I added equivalent series resistance. That's the name of the article on Wikipedia. Go look it up. Equivalent series resistance, to add reality to the simulator, because he didn't have it. LT Spice already has that feature built into it by default, and then you can modify it as well. But Paul Falstad didn't have it at all, and so that without it, it makes it much easier to come up with free energy circuits. But with it, it makes it a little more difficult. But this circuit, it sings in both versions of reality. It doesn't make any difference whether you have series resistance inside your caps and coils or not. But I tested under both, and it works just fine. It works a little more restricted in terms of what kind of wiggle room you've got to work with when you're working with equivalent series resistance in the circuit simulation, but it still works. You can still get it to function quite nicely. Unfortunately, the impedance increases, I would imagine, because the voltage goes up. So actually, no, that's actually better, because instead of the voltage being less than the amps, it surpasses it slightly. And that's more realistic, and that's exactly what we want. We want realism. We want to deliver what we're accustomed to. So Greg Tuntlin is a guy on YouTube who wanted, he specifically said, give me a circuit that'll give me 200 amps and 144 volts for my EV conversion. And I guess I've succeeded, maybe. There is one caveat to the circuit, I must say, despite all of its benefits and good points. There's one caveat, and that is, besides requiring a computer to manage this thing, if you don't want to, monkey with it manually to get it to run it. But in Tesla's day, I'm sure that they didn't have car computers, so I'm sure he had to do it manually. But the one caveat, aside from that, is that that's a minor thing, so I don't consider it a second caveat. The one main caveat is that it's a bit randomized when you're jimmying it to increase its power gain, to increase its current gain. It's not its power, excuse me. It's not the watts. To increase its current gain, it's a bit randomized. You don't know. I mean, there is a certain window, maximum and minimum slightly, every time it jumps up See, what happens is when you lower the capacitance, you lower the amperage. But when you raise it, more often than not, you will raise it greater than it was before. Greater than what you had lowered it. So you end up with a gain. But sometimes you can gain too much, and it depends how much you leapfrog around. So if you go down, I tried out, I was jimmying up and down between 1 farad or 10 farads and 1 or 10, I believe it's called yocto farad. I mean, that's pretty low. Or is it yodo? Yoda? I think it's yocto. I don't know. I get them mixed up. Lowercase y. You know, scientific notation, the lowercase y is really low. It's a lot of zeros to the right of the decimal point. A lot of place values to the right of the decimal point. I think it's either 18 or 24. I want to say 24 zeros to the right of the decimal point. That's pretty low. And that tends to give you huge leaps of increase of current when you raise it back up to either 1 or 10 farads. 10 is the limit. I don't go beyond that because it doesn't really seem to do anything. And so you may not want to use such a low value. What I like to use is, at first I'll use I'll go down to milli farads, and I'll go back up, 10 millifarads maybe, or 1 millifarad, and then I'll go back up to 1 or 10 farads. And then when I'm approaching my target, and my target, I look for the scope of the aerial, and I target 60 amps is my target. Even though I want 200 on the load, my target though on the aerial is 60 amps, more or less, slightly less, or slightly more, maybe 80 at tops, maybe 30 or 40 minimum, and then 80 tops. And when I find that, when I get that current, then I know when I engage the load, it should have 200 amps or slightly more. Most of the time, but sometimes it doesn't always happen that way. Sometimes the relationship between the two sides of the transformer don't always work out that way, and you end up with a bit more, like 600 amps on the load. But if you use the y, the lowercase y scientific notation value of capacitance on the controlling capacitor on the right-hand side of the transformer, when you jimmy downwards, you could end up, when you jimmy it back up to 1 or 10 farads, you could end up with several thousand, amps on your aerial. And it's possible the sky's the limit. Infinity is the limit. You can take it as high as you want to, jimmying it up and down. Now, what I did was, originally, I didn't jimmy up and down. I just kept increasing the farads on that right-hand capacitor, and that increased its power gain. Excuse me, I keep saying that. I'm sorry, it's my error. It's current gain. But then I thought to myself, that's not practical. So then I thought, well, gee, I'm trying to focus on operator engaging the circuit here. It's not a static circuit that just sits there and does everything for you. You've got to monkey with its values of its components to make it work. Why not jimmy the value of the capacitance of that right-hand controlling capacitor, what turns out to be a controlling capacitor, up and down, up and down, up and down, and it works like a charm. It takes patience, though. You got to, at first, you don't see any changes happening anywhere in any of your components. And yet you keep going up and down and 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 up and down. And so you get like, huh? Do I have the patience to wait for this? And I would say to myself, just stick with it. Just stick with it. Just keep doing it. Come on, keep doing it. It's worth trying. You'll never know if you don't exhaust all possibilities when designing a circuit. And that's basically the approach I take, which is why it takes so much effort and time and work. But it paid off because I realized that Tesla's invention is actually valuable because we can literally benefit from it by amplifying current in a circuit. Now, the Wikipedia article said high frequency, he used it for high frequency and high voltage circuits, but it's the current that we gain in its use, not the voltage. Sure, you could change the frequency by where you leave it at set to when you engage the load. And so what happens is, if I overshoot my gain of current, then or if I come short of it, I may have to raise it. And you know, actually I start with 10 farads and I lower it to 10 millifarads, up and down, up and down, up and down. And then as I approach it, I don't go all the way down to 10 millifarads. I might just go down to 1 farad, and then go back up to 10 farads, and then go down to 1 farad, and then back up to 10 farads. And then if I overshoot, I might lower it. Hopefully I didn't overshoot too much. Then I'll lower it to get to the value of current on the load that I want. No, excuse me, current. Well, actually, if the load is too much, then I disengage the load and then go back to monkeying with the capacitor. So I'll drop it slightly. So in one example, I dropped it down to 5 farads, and then I re-engaged the load, and I had it right where I wanted it at, 240 amps and 160 volts in the simulator that did not have equivalent series resistance. In the equivalent series resistance, I think the voltage was up at, actually the amps was lower. It was 180 amps, which makes sense because, you know, there's series resistance inside the coils, so of course it's going to be less amps. But the volts was higher, which also makes sense when you have resistance. And volts was up at, I think it was 300 volts, 300 plus. Which is a little high, but it's only double what Greg Tuntlin had asked for, so that's not bad. So I consider myself to be pretty successful, by and large. Give and take, a little wiggle room, for this very crude first beginning of a very simple circuit that actually manages to amplify current somehow. I don't know why, but according to Eric Dollard, he explains why. Because electricity is made up of constituent parts, and it's not a singularity, and it's by varying an electrostatic contribution or electrostatic field to a magnetic field that the synthesis of electricity, or in this case the synthesis of current, occurs. And I thought we had to immerse a magnetic field in some kind of environmental electrostatic field, but I was wrong, because I actually have this controlling capacitor on the right hand side connected directly to the transformer, the right hand coil of the transformer. So it's inside the circuit that the electrostatic field exists, and the magnetic field is nearby surrounding the coils. But in actuality, the electrostatic field terminates one end of its line of force on the circuit components, such as the capacitor, dielectric, or plates. No, on the dielectric, actually. The other one is somewhere off in space somewhere, to all the other objects in creation. Because all objects in creation are connected by longitudinal magnetodielectric waves. It's the transverse electromagnetic waves that don't terminate on anything and just orbit continually around points in space that they are associated with. And those are the ripple currents that we see on the surface of a pond, or the transverse electromagnetic waves that standard conventional theory tends to harp on and focus on a lot. But there's this other kind of wave that does not travel in space, unlike a ripple wave. It's a shock wave that travels in counter space. And this counter space is what we call akasha in the Sanskrit. It's also called, well, akasha is actually the cover term for both space and counter space. No, actually it's called the ether, or counter space if you prefer. The realm of imaginary numbers. And complex numbers, because you can't measure counter space, the values of what goes on there. But the longitudinal magnetodielectric wave terminates, the two ends of that wave terminate, well, it's not a circular orbital wave that looks like a ripple wave. at the boundary between two mediums, such as the boundary between water and air on a lake, for instance. Instead, it's the depth, the deep interior of a medium that's undergoing compression, or its opposite, vacuity. Extreme vacuity or extreme compression, either one. A tsunami wave is a compression wave, but you can also have a compression-style behavioral wave, a longitudinal wave, occurring in empty space, because it functions the same way when you lack pressure versus when you have too much of it, such that you can't compress the medium any further. The behavior of that longitudinal shock wave is the same, and that wave terminates on the two endpoints, the destination and the what do we call it? The home plate, where it came from. Those two ends are where it terminates on, and it turns out that circuits send out these longitudinal waves in all directions, and they terminate on all the other objects in creation. So everything is connected longitudinally through counter space, through the ether. And electricity literally unites all of us in this web of interaction. Of course, it's very loosely coupled in the sense that it's very weak. If it's outside the circuit, then we call it the circuit's environment. But it's not zero interaction. There's some interaction all the time between all electrical circuits and their subcircuits in creation. It's just a question of whether or not it's a loose coupling or a strong coupling. If it's a strong coupling, then we can say it's part of the circuit. If it's a loose coupling on the strong side, then it's adjacent to the circuit. It's just loose. It's considered part of the circuit, even though it's a loose coupling. And of course, we have that in a transformer. Can be a strong coupling or a loose coupling. In my circuit, of course, the two coils are loosely coupled. Anyway, I think that's pretty much everything. And then we keep the coupling between the two aerials as loose as possible. Hopefully not coupled at all. That's best. Uncoupled between them. But of course, how much is zero, in terms of coupling between two aerials that are 3 feet apart, with the air flowing between them at a perpendicular? You can't get to zero. You can approach it, but you can't get there. In the concrete world, it just doesn't exist. So you see, zero is not absolute in the concrete world. Only in the abstract world of the idea of zero is zero absolutely zero. So this is the opposite infinity to infinity, because we know in the concrete world all we can do is approach infinity. We can't reach it anyway. Well, it's the same thing with zero. It's the other type of infinity. And this is expressed in terms of 1's complement arithmetic, which is what? Assembler language, assembler computer language at the machine operating level of the register and bits and bytes and logic gates operates at. And this is also the Vedic expression. Sorry, I'm losing my voice. I better shut up in a minute. Purnamida, Purnamidam. This is full, that is full. Two fullnesses. Both are full in their own unique way. Yang is full, but yin is also full. The nihilists of Nietzsche and the existentialists would say, no, it's the void. But that's also a type of fullness. It's just fully empty. But that's an abstraction, an abstract idea. In the concrete world, all we can do is approach those two infinities, or either of those two infinities. Not both at the same time, but either one or the other. But we can't ever reach it. And so it's a hyperbolic limit. The hyperbolic function of division, if you divide one number by another and graph it on a Cartesian coordinate XY axis, two-dimensional plane, you get a hyperbolic curve that never reaches the x-axis or the y-axis. Those two axes are the limits of that hyperbolic function. They are considered the asymptotes of that hyperbolic function. But the function itself can only approach infinity in either one type of infinity or the other, the zero limit or the infinity limit. But they can never reach it. in the concrete world. Even in that abstract world, the hyperbolic function can't reach it. But in the concrete world, we can't either. And so it's okay to think about infinity because it does govern our world, but we can't reach it. You know, our concrete world that our bodies, you know, move around in, but we can't reach it. But we can exercise the option to manufacture free, or excuse me, amplify for free current. And we can also reuse voltage without spending any by draining it to convert it into current. So that's why we separate the two. That's the secret to free energy, is we separate the two. We reuse the voltage, but we somehow gain the current by synthesizing it from its constituent parts. And I suspect that's also a reuse situation as well, or else we wouldn't be able to get away with it, would we? So there's a lot of recycling going on with electricity, and it doesn't surprise me because it's not the same as burning a log of wood in a fireplace. That's a consumable because we're converting wood into ash and charcoal, in which we can still burn the charcoal somewhat, but the ash we can't. It's already fully burnt. And so we got to go buy some more firewood and clean out the fireplace of all the ash accumulating there so that we can have a nice fire. But it's not the same with electricity. The relationship is not the same between what we are spending, supposedly, and the energy that runs the thing is something else entirely. So we have to get that straight in our brain, that electricity is not a consumable product. It is something we can reuse again and again. But the conversion of what we are consuming or losing is the current. That is what we are losing. That's what heats up the coil and dissipates heat into the environment, and depletes the current in our circuit, and then we have to go fetch some more current from somewhere. And so if we fetch it from a battery, a voltage source, we deplete the voltage on that battery. Well, I don't want to do that. I want to reuse the voltage on that battery. So I don't go to the battery to get my current. I don't go there. I synthesize it inside the circuit. I only go to the battery to either start the circuit, very little drainage to get it going from a cold start, but when I want to raise the voltage on this voltless, for the most part, very low voltage situation, then I simply borrow it. But I give it back because I use AC. So I take it and I give it back. I take it and I give it back. And so that battery capacitor battery sandwich never loses its voltage, and simply gets a massage in exchange to keep it conditioned, to keep it healthy, to keep its state of charge and its freshness, its youthfulness, vigor, alive and well for as long as possible, as the materials of construction of that battery will allow. So I think it's a pretty good crude circuit. Crudeness aside, I think it's pretty good. It's also very simple and very elegant in how it approaches the situation.